Okay, this is our first video recording. Today we're going to be talking about probability. We will be having a continuous conversation in this class about why we need to use probability and how to talk about the thermodynamic properties of matter effectively. But for now, I just want to talk about what probability is, how we should think about it, and effectively have a refresher of the basics that you may or may not be familiar with. Maybe you've learned about it before but stopped thinking about. Maybe you've never really thought about probability in any particular way. Um, so our job is to put everyone on the same footing, and the first thing we're going to do is to discuss what probability is, how to think about it, and ultimately we'll talk about how we calculate it by using a couple of simple examples that will be familiar to you. So first, when we start talking about probability, you're probably starting to immediately think of odds. Maybe you're thinking betting odds. Maybe you're thinking questions like what is the chance, what is the likelihood that you pull out a particular card out of a deck of cards? What is the chance that you're going to have a tails or a heads when you throw a coin? What's the chance of getting a certain die combination in some kind of a gambling game of some kind? So that's the usual way in which we've thought about probability. What do we mean by that in that particular respect? For example, I think most of us will agree that when we say that flipping a coin that is ideal in the sense, the probability that you'll get a tail or a head is 1/2. That is to say, the probabilities are equal, the likelihood is equal, and you expect to half the time get a tail when you throw a coin and half the time to get a head. Now, what does that really mean? Mathematically, this is what we have in mind, and we have to be really careful about this. We associate the probability of obtaining a head or a tail in the following physical sense. We imagine flipping a coin many, many, many times, and we look for the number of times that out of all the possible outcomes after many trials, let's say after n trials, where n is very large, we obtain a certain number of heads. So this is what we would do. We imagine throwing a couple of, or a coin many, many times over, and we imagine evaluating this quantity, frequency with which, let's say, a head is observed. A head is observed after n trials. And by trials, we mean coin flip. This frequency, we imagine evaluating after doing many, many, many identical trials. That is to say, we take the limit as the number of trials goes to infinity. So this thing is equal to the limit as the number of trials goes to infinity of the number of times that you observed a head after a coin toss divided by the total number of trials. This is what we mean when we say the probability of obtaining either a tail or a heads. We are physically imagining repeating the same experiment, tossing the same ideal, identical coin many, many times over with no bias, so in the abstract ideal sense, and recording the outcome diligently after many, many possible tosses. We calculate this quantity as the ratio of the number of times your outcome of interest was observed, in this case a head, divided by the total number of trials that we flip the coin over. And we believe that this number approaches 1/2. That is to say, 50% of the time you expect to get a head, and 50% of the time you expect to get a tail. Now, if n was something like 10, or even if n was something like 100, do you necessarily expect to find half of them, of the outcome being tails, half of the outcome being heads? No, not necessarily. In a trial or a series of trials of 10 times, 10 throws, you might in fact find 3 heads and 7 tails. Another time you repeat the 10 trials, maybe you'll find 4 and 6. Maybe sometimes you'll find 5 and 5. 1 and 9 every once in a great while. And so you won't necessarily expect to find half of the heads in the total number of trials after a finite number of tosses. We really have to imagine that this is done over and over and over again, so this is really enormous. And only when this has become enormous, we find a number that in this limit approaches 1/2. And this is what we mean by the probability of obtaining the outcome head out of a total of 2 possibilities, a tail or a head. Similarly, we can imagine the probability of obtaining, let's say, the face 1 out of a 6-sided die. Now we know that a 6-sided die has 6 sides labeled 1, 2, 3, 4, 5, 6. We imagine an ideal die where no face is preferred. We imagine tossing this die. And when it lands, a number is found. That number is recorded. And after many, many, many identical die tosses, you record the number of times a 1 was observed. And we feel intuitively that given that no face is special, and given that there's a total of 6 faces, you expect to find 1/6 of the time a 1. But again, this 1/6 probability of obtaining a 1, or 1/6 probability of obtaining a 4 or a 5 in a given hypothetical die toss really imagines a sequence of n identical die tosses, the outcome recorded, the ratio found in the limit as the number of trials goes to infinity. And so this frequency of obtaining the outcome that you're asking about, or the number of times the outcome was obtained divided by the total number of all possible outcomes after a series of n trials, we associate with the probability of that specific event. So this is perhaps not that surprising. But I think it's also worth thinking a little bit further about the meaning of the word probability from the perspective of there are circumstances where performing n trials, where n is very large, is not only impractical but actually impossible. And so what do we think about, what do we mean when we say the probability in those circumstances? So let's consider one of those circumstances. One of them will be very familiar to you. This is an example that's used by Bayerlein's book that I mentioned in the syllabus, and that is, of a student taking an exam. Now imagine you took an exam, you're feeling okay about it, you feel like you're, maybe got the majority of the problems right, you come out and you start having a chat with your classmate, and your classmate asks you, well, how do you think you did? What do you think the chances of you getting an A is? You say, maybe there's about an 80% chance that I got an A in the test. Maybe there's about a 60% chance that I got a B. I'm sorry, an A plus. Maybe there's a 90% chance in your estimation that you got a B. Now, what does that mean? Do you imagine that you take n identical exams in n parallel universes, where the number of universes goes to infinity? You then record your score at the very end of your test, and then in that limit, as the number of parallel universes or independent U's taking the same identical exam on the same date and time, is that frequency of times that you got a B, or the frequency of times that you got an A, and so on, should we think of that as the probability? Problem is, it's ludicrous, of course, to attach probability to this impossible way of repeating the same experiment. Nevertheless, we feel some comfort, some sense in being able to quote the probability of such an event occurring, even though it only occurred once. So this suggests that this idea of a frequency as being synonymous with probability in the limit as the number of experiments or trials or measurements is taken over and over again, in the limit as n goes to infinity, maybe that's not the only or the most general way to think about probability. And so I'm going to give away the answer of how we should modify our understanding of probability that we'll connect to later on when we talk about why we need probability in this class. Excuse me. When we try to reconcile this kind of interpretation of probability as the frequency of a certain outcome, or the ratio of the number of outcomes to the total number of all possible outcomes, with the fact that we are able to speak about the notion of probability in circumstances where this is impossible to do, what it says once again is that we need a slightly more general notion. That general notion is to associate with probability not necessarily from the outset this idea of a frequency, of a repetition of an experiment many times, but as a very specific logical construct, that logical construct being called um, um, degree of rational belief. Sorry, my brain blanked for a second there. Degree of rational belief, that is to say, in the absence of certainty, in the absence of knowing for a fact how a coin will land, in the absence of knowing for certain how you actually performed on the exam because the exam hasn't been graded yet. This idea that you have some rational belief about the likelihood of a certain outcome. And that rational belief might be supplied from different places, directions, sources in a sense. Now, your degree of rational belief in your having gotten a B or an A on an exam has to do with your perception of perhaps how you've seen the problems. Maybe you've encountered them on the homework before. Maybe you were able to reason through it and your answer made so much sense that you just feel quite certain that it was the right outcome on most questions, but not every one. And so we feel compelled to assign this probability in this case. Whereas in this case, we are assigning a degree of rational belief in obtaining either a tail or a head. What we're saying is that in fact, because the coin is perfect, and because there's only two possible outcomes or two sides to the coin, we have no reason to prefer any one of these outcomes. And so our degree in rational belief is actually identical in whether it's a tail or a head. We don't think any one is preferred. And so we expect that half the time we'll get a head and half the time we'll get a tail. Now, of course, in the end, these definitions converge in this example of a head or die throw or a coin toss. But it's very clear that by using this example of a test, that the notion of a probability has to be somewhat modified. And so that's the first thing that we want to mention, is the idea behind a probability. Now, how do we mathematically make a statement, a definition that we're going to go on and can come back to and use and reuse and be comfortable with that definition? Here's what we're going to say. So I'm going to erase this, and we're going to define probability, having understood these subtleties that we just discussed, in the following way. We're going to imagine that there's going to be some set of inferences. For example, an inference might be after a coin toss, a head is obtained. Another inference would be after a coin toss, a tail is obtained. Perhaps there are many different kinds of inferences. The inference that after a single die throw, the number 5 is obtained on a 6-sided die. Or the inference after a single die throw, the number 3 is obtained. Or the inference that after 2 die throws, the sum of the two faces is 10, for example. And so these are the kind of inferences that we're talking about. And so here's how we're going to define probability. I want to be close to the notes here. So I'm going to look back on my notes to be consistent fully with the definition there. So this is page 1. So we define the probability which will give the letter and continue to use capital P of event A, whatever A might be, or in other words, of inference, whatever that might be. For example, that I obtain a head after a single coin toss. We're going to define this. The 3 equality sign is going to mean defined as. So not just equals, but stronger. This is the definition of this quantity. So the probability of event A is going to be defined as the number of outcomes for which A takes place, or we might say A is true, or A is obtained, observed, however you want to put this. The number of outcomes for which A is true or A takes place divided by the total number of outcomes. For example, in a series of 10 coin tosses, the total number of outcomes is going to be 10, because after every coin toss, some inference is found, some outcome is observed. The number of times a head was obtained is going to go in the numerator, whereas the number of times a head is obtained plus the number of times a tail is obtained, i.e. the total number of outcomes, goes in the denominator. And that's fairly self-explanatory. Now, the set of all possibilities has a name. Again, we're following the lecture notes pretty closely here. And the name that goes along with the possibilities or the inferences that are possible under a certain hypothesis, under a certain scenario, in this case is called the sample space. So for example, for a trial that looks like one coin toss, the sample space contains two elements. So it's a set. Sample space is set of all possible outcomes. So here the sample set would be a head and a tail. And so number of outcomes is 2. Or the size of the sample set is 2. Now, I would like to stop here before we talk about how we're going to use this definition. But what I want to stress is that this is going to be the operational definition of probability that we use in this class. This is closer in spirit to the frequency definition that we just talked about. So this idea of forming ratios of the number of outcomes as being, in a sense, logically derived from the idea of degree of rational belief. And so the degree of rational belief as what probability philosophically represents should always be in the back of our mind. But as far as finding numerical values, we're going to be using an expression that looks like this. And what we're going to go on to do is to use the coin toss example a little bit more, think about the idea of tossing the coin multiple times, but this is the idea, the philosophical kind of understanding that should go along with the notion of probability as we mention it. We'll have a lot more to say about it as we go forward.